Mm. Good morning, Kiran. Am I audible?
Yes, sir.
Yes,
You're
sir.
audible.
Good morning, sir. Principal, sir. Good morning.
Sir, good morning, sir. Saptam, ma'am. We'll start, ma'am.
Okay. Hello, everyone. A very good morning to one and all. Before starting this session, let's start with a prayer song by our student Divyashri.
महागणपतिं मनसा स्मरामि महागणपतिं मनसा स्मरामि महागणपतिं वसिष्ठवामदेवादिवन्दितमहागणपतिं वसिष्ठवामदेवादिवन्दितमहागणपतिम्.
Principal of MLRIT, Dr. K. Srinivas Rao. Let's welcome Dean of MLRIT, IQAC Head, Dr. V. Radhika Devi Ma'am for this program. I welcome our motivate you and convener of this FDP, Dr. A. Balram, Professor and Head of CSE Department. Now I welcome our coordinator, Dr. Azmira Kiran, Assistant Professor of CSE. Now it's my great pleasure to welcome today's resource person, Dr. Tanmay Kumar Sir, Behera, Professor, Department of CSE, NIT, Mizoram. Finally, I would like to welcome all the coordinators, advisory committee, organizing committee, faculty members of MLRIT, faculty members of various colleges, research scholars, and PG scholars. Welcome all. Now, I request Dr. Azmira Kiran, coordinator of today's program, to address the gather.
Thank you, ma'am. Honorable Chief Patrons of MLR Institute of Technology, Hyderabad, Sri Marri Lakshman Reddy Garu, Chairman, Marri Rajshekar Reddy Garu, Secretary, Srimati Marri Mamata Reddy Garu, Treasurers, and today's chief guest, young and dynamic entrepreneur with a strong foundation in both business and academia, Miss Marri Reddy Garu and Marri Dhiran Reddy Garu, Director of MLR Institute of Technology, Hyderabad. Dr. K. Srinivas Rao Garu, Principal, MLRIT, Dr. V. Radhika Devi Garu, Head, IQAC, and Head of the Department, Computer Science and Engineering, Dr. Allam Balram Sar Garu, and respected heads of various departments, and my dear colleagues and wonderful participants. Very good morning to one and all. I am Dr. Ajmera Kiran, coordinator of the 1 week online faculty development program on artificial intelligence, machine learning, and data science with research applications, being organized by the Department of Computer Science and Engineering, MLR Institute of Technology, Hyderabad. I warmly welcome you to all this program. At the outset, I extend my heartfelt thanks to the management and director of their constant encouragement and unwavering support in organizing such enriching academic initiatives. The objective of this FDP is to provide in-depth understanding and practical insights into core areas of artificial intelligence, machine learning, and data science, along with their applications in research. The program is designed to introduce participants to both theoretical foundations and hands-on tools essential for current trends in artificial intelligence and data-driven technologies. This training program offers a unique platform for researchers, industry experts, and academic professionals to share knowledge, best practices, and innovative research findings. Participants will gain exposure to essential topics such as classification, regression, prediction, deep learning fundamentals, and statistical modeling. We are pleased to share that this year we received an unwavering response, more than 500 registration within a very short time frame. This remarkable interest reflects the growing relevance of the topics covered, as well as the reputation and excellence of our institution. Much of this research is organic, with many participants discovering the program simply through our website. The resource persons for this FDP are highly experienced and come from prestigious institutions such as IITs, NITs, and state universities. And we are confident that the sessions over the next 6 days will be highly engaging and beneficial to all the participants. Thank you all for being part of this event. Over to you, Madam Saptami Madam.
Thank you, sir. Now I request Dr. A. Balram, Head of Department of CSE, convener of today's program, to speak few words about the department.
Thank you, Saptami. I'm audible.
Yes, sir.
Good morning to all of you. I feel proud and glad to welcome you as we begin this program, 1 week faculty development on artificial intelligence, machine learning, and data science with research applications. Today, we all of know that technology is advancing at an extraordinary pace. New ideas, tools, and methods that are transforming every field from education and healthcare to business and research. Among these, artificial intelligence, machine learning, and data science have emerged as some of the most powerful and impactful areas. These technologies are not only shaping industries, but are also opening up new horizons for research and innovation. As a teacher and researchers, it is our responsibility to keep pace with these rapid changes. We must continue to learn new skills, understand latest trends, and brings that knowledge into our classrooms and research labs. By doing so, we empower our students to be ready for the future and inspire them to think beyond the boundaries. So our Department of Computer Science Engineering has always taken pride in staying ahead of these curves. We are committed to providing our students and faculty with the knowledge and tools they need to excel in the ever-evolving tech landscape. Initiatives like these faculty development program reflect our dedication to our continuous learning, skill enhancement, and research excellence. This program has been carefully designed to help all of us strengthen our understanding of both fundamental and advancement concept in AI, ML, and data science. It will also provide practical insights into how these technologies can be applied effectively in teaching and research. Over the next few days, we will learn from experienced experts who will shape their valuable knowledge, practical examples, and best practices. Through this program, I hope each one of you will gain confidence to adapt these modern technologies in your teaching and research work. This will help us create more engaging and relevant learning experiences for our students, motivating them to develop innovative solutions to real world problems. I truly believe that our Department of CSC will continue to grow stronger through such initiatives. By encouraging the faculty to learn and adapt, we create an environment of curiosity, collaboration, and innovation that benefits our students and the institution as a whole. So, in conclusion, I wish all the participants a week filled with meaningful learning, inspiring ideas, and fruitful discussions. Let us make the best use of this opportunity to upgrade our skills, exchange knowledge, and contribute to the progress of our students, our research, and our institutions. Thank you and all, and I wish this program great success. Over to you, Saptami.
Thank you, sir. Thank you for sharing your wonderful words. Now I feel grateful to have the presence of our beloved principal, sir, Dr. K. Srinivas Rao Garu, to inspire the participants.
Thank you, Saptami. Am I audible?
Yes, sir.
Respected faculty members, distinguished resource persons, participants, and organizers here, and head of the department, a very warm good morning to everyone present or here. It gives me a great pleasure to welcome you all on the 1-week faculty development program on artificial intelligence, machine learning, and data science with the research application. So first of all, I would like to congratulate the organizing team for taking this important step towards the growth and development of the faculty. I would also like to extend my sincere gratitude to the eminent speakers and the experts part of our daily lives and are driving transformation across almost every industry. In this rapidly evolving world, it is our responsibility as the educators to keep pace with these advancements. We must ensure that our knowledge, skills, and teaching methods remain up to date. Only then we can equip our students to face the challenges and seize the opportunities of the future. So this faculty development program offers a wonderful opportunity for all the faculty fraternity to learn, not only faculty fraternity, research scholars also, to learn, explore, and gain in-depth understanding of these technologies. The session planned over the next week will cover typically practical applications of practical applications and real world case studies. And I encourage all participants to make the most of this valuable opportunity. I firmly believe that the knowledge gained through this program will empower our teachers to bring fresh ideas and innovative teaching strategies into their classroom. It will also inspire new research initiatives and also foster opportunities for interdisciplinary collaboration. Continuous professional development is the backbone of any forward-looking education institutions. In this aspect, MLR Institute of Technology is the one among the educational institutions which will promote professional development of the faculty. When our teachers grow, our students benefit, and our institution also progresses. By staying updated with our latest trends and technologies, we also set a good example for our students that learning never stops, regardless of age or experience. And I sincerely hope that by the end of this program, each one of you will feel more confident in integrating artificial intelligence, machine learning, and data science into your teaching and research. And I wish you all the best to all the participants and the organizers. And this program, finally, I must thank Mr. Tanmay Kumar Behera, NIT Mizoram, and all the resource persons. I think today's resource person is Tanmay Kumar Behera. So once again, I welcome to this faculty development program, and for all the participants, once again I wish you all the best. Thank you. Over to Saptam.
Thank you, sir. Thank you for sharing your inspiring thoughts to us. Now I request everyone to switch on your camera so that we can have the group photo. I request all the participants to switch on your camera so that we can have the group photo.
Yes, ma'am. Done.
Okay. It is my privilege to deliver the vote of thanks on behalf of Department of Computer Science and Engineering, MLRIT, Hyderabad, at the inaugural of one-week faculty development program on artificial intelligence, machine learning, and data science with research applications. First and foremost, I express my sincere gratitude to the Honorable Chief Patrons of MLRIT, Sri Mari Lakshman Reddy Garu, Chairman, Sri Mari Rajashekar Reddy Garu, Secretary, and Srimati Mamta Reddy Garu, Treasurer. Thank you for your constant encouragement and visionary leadership. A heartfelt thank to our directors of MLRIT, Mrs. Mari Shreya Reddy Garu and Mr. Dhiran Reddy Sir, for graciously accepting our invitation and taking time. And also we had all necessary resources to make this event a grand success. We are deeply grateful to our principal, Dr. K. Srinivas Rao Garu, for his inspiring words and constant encouragement. Sir, your study guidance and leadership continue to be a strong pillar for all our academic efforts. Thank you for your ongoing support. I would also like to thank Dr. V. Radhika Devi Garu, Dean IQAC, for her kind support and encouragement. A special note of thanks to our head of department, Dr. A. Balram Garu, who is truly the backbone of our department's initiatives. Sir, we sincerely thank you for your continuous motivation and for meticulously planning the resource persons and structure of this 6D FDP. I extend my heartfelt thanks to all the head of departments across MLRIT for their support and cooperation, which played a vital role in the successful organizing of this FDP. A sincere thank you to all the resource persons for accepting our invitation and sharing your knowledge. Your sessions have enriched our participants and creating an engaging intellectual environment. Lastly, I thank all the deans, faculty members, research scholars, and participants for their enthusiastic response and contribution to success. Once again, thank you all for being a part of this program. Wishing everyone a full of productive learning and collaboration. Thank you all. Uh,
Thank you,
within
Saptami.
within 5 minutes, thank you, sir. Within 5 minutes, the session is going to be start.
Thank you, madam.
Uh, Welcome back once again to 1 week faculty development program on machine learning, artificial intelligence, and data science with research applications. Now, I take privilege to read today's resource person, Dr. Tanmay Kumar sir's profile. Dr. Tanmay Kumar Behera is currently working as an assistant professor in the Department of Computer Science and Engineering at the National Institute of Technology, Mizoram, India. Prior to that, he also served at Dr. B.R. Ambedkar National Institute of Technology, Jalandhar, Punjab, India, as an assistant professor. He also worked as a postdoctoral research fellow at TIH IIT Patna Extension Center, established at National Institute of Technology, Rourkela, India. He received his PhD and MTech degree in Computer Science and Engineering from National Institute of Technology, Rourkela, and Veera Surendra Sai University of Technology, Burla, India. His research interests include machine learning, computer vision, drone vision, medical image processing, and visual surveillance, in which he has published research articles in top tier research journals. He also filled multiple intellectual property rights in the domain of his works. He also serves as a reviewer in many top tier research journals such as IEEE Transactions on Circuit Systems and Vehicular Technology and IEEE Journal of Biomedical and Health Informatics. Sir, I feel very grateful to read such a great profile, sir. Now I request Dr. Tanmay Kumar, sir, to take over this session.
Okay, thank you. Thank you very much for the introduction. Should I screen right now? Am I audible?
Yes, sir, you're audible, sir.
Yes.
Welcome you, sir. Tanmay, sir.
Dr. Audible?
Yes, sir, you're audible, sir.
Yeah. Thank you, sir. Thank you. The one thing I'm guessing that due to the slow connectivity, the voice is with like you're getting the voice lately. Maybe.
Your
Is my screen
voice.
visible?
No, sir. Sir, actually, your voice is breaking.
Okay. Yeah, Dr. Kiran, am I audible right now?
Sir, could you please rejoin, sir? Actually, your voice is breaking. So if you rejoin, means it will come.
But hi, Dr. Kiran, am I audible right now?
Yes, sir. Now it's fine, sir.
Yeah, got it. Let me share my screen, right? Is it visible?
Yes, sir.
Yeah, I'm really sorry because of the internet issue. Yesterday was quite a heavy rain here, so due to which we are having some internet issue right away. So for that thing, I'm keeping my camera off so that the screen would be visible to all of you perfectly. Okay.
Thank you, sir.
Yeah. Okay, so very good morning, all of you. Thank you for having me here in this grand faculty development program of 1 week on the topic of artificial intelligence, machine learning, and data science with a very applications perspective. So to be here, glad, and I would like to convey my thankfulness to Dr. Kiran, sir, and as well as the HOD of the HOD CSE of MLRIT Hyderabad, Dr. Alam Balram, sir, for inviting me into this particular FDP program. Okay, so basically before starting this topic, as you can be able to see it, that it's based on some of the research use cases of UAV-based remote sensing image analysis. So if you will see that this particular topic I have kept here for this particular program is due to, like, I would like to have this brief information with respect to whoever the faculty members, those who would like to start this particular topic or like to work in this particular research area, or those faculty members who are interested in pursuing their PhD in this particular research area, they would have a brief idea of how they can actually start proceeding towards getting this particular research topic and can work, because this is one of the, I would rather say, the domain, that open domain for all the computer vision researcher, or I would rather say the machine learning or deep learning or the AI researchers, that they can start proceed with this particular research and have a great amount of scope, because it has a wide range of research applications that you can like, you have to just imagine it, and you can put forward in whichever the research application you want, and you can start doing the research, because as you know, the UAV itself is a huge market, and recently government of India has actually started some initiative towards this particular research area of UAV, with respect to multiple schemes such as the PLA scheme, that is the Production Linked Initiative Scheme, and Drone Shakti Initiative schemes. So basically, they have sanctioned a amount of like 1,261 crore rupees for investing in this particular research area, so that the Atmanirbhar Bharat can be achieved with respect to the drone technology itself for our country. So basically, this is one of the research area on which of all these things, in dive deep idea, that our target was that as you know that remote sensing device itself works with a very less amount of computational and storage, I would say, resources, right? So primarily, if you want to deploy your deep neural network model to perform on that particular device itself, will require you to embed more amount of resources in terms of storage as well as the computational efficiency, right? Which we cannot do. Primary thing is that, like, we can, but not. It is up to an extent, right? So that is why we are mainly focusing on reducing these parameters of a particular architecture. Also, these are some of the issues that you will definitely going to find it in a classical deep learning architectures, because they are quite huge in terms of the parameters they are carrying with. So they definitely have to suffer with respect to degradation problem, the vanishing gradient problem. Obviously, the overfitting is still there in much of the models, right? Now, if I am saying this trainable parameters reduction, these are nothing but parameters that represent a neural network. What are the parameters? So basically, they are nothing but the weights and biases, right? So you have to reduce them in such a way that they should overcome with respect to these three of the issues. Also, they are not compromising the accuracy of that particular architecture, right? Yeah. And also, we have found out that there is a scarcity of this semantic segmentation dataset. This particular object extraction tasks. Now, these are known as intrinsic challenges or internal challenges. You will be able to find definition. Now, this is a computer. So the environmental effect that can give you this kind of challenges. So we have identified a few of them, and while developing the dataset, we'll try to get all these challenges in our dataset itself, because they are definitely going to hinder the process, right? Now, and we have identified the objectives. Now, research gaps have been identified. So the motivation have been identified from that. Now, the objectives you have to identify on top of those research gaps that we have already discussed, right? So these are the few objectives that we have focused on. Now, this particular slide here. So as I told, that my primary discussion here is that for all the faculty members out here, those who want to start a research work or who wants to pursue a PhD in this particular domain. So basically, if you'll see, this whole slide represents the whole work that I have conducted during my PhD and post-PhD, right? So here, if you'll see that we have started surveying multiple research papers and the data sets out there with respect to this segmentation thing, right? That is the aerial image segmentation. And we have analyzed the satellites part as well as the UAV part. Now, you have to justify your work first, because satellite images are the widely available images in your domain. Now, why you deep dive into this particular UAV itself? So the question may come. So for which we have first explore this particular satellite-based remote sensing image analysis with respect to road and vegetation extraction. Now, that give us the insight of why we should move towards this UAV-based image analysis portion, right? As you know, if you will consider some of the scenario, let's consider the example from the vegetation part. Now, the vegetation extraction has the application in terms of precision agriculture, the forest management, and you will share that urban planning as well, right? Now consider the example of a precision agriculture. Now, do you think that the satellite images are good enough to provide you uh, to identify the diseases a particular leaf is suffering from in a particular tree? It's totally impossible, right? We may have but still they cannot be employed for a for developing a good precision agriculture uh, task, right? So that is one of the example. So we are transforming over here. Now, as our case, we have one task with respect to the vegetation extraction, right? So it satisfies that. Along with it gives us the uh, idea or the insight that how exactly the satellite images, based image analysis with respect to these two objects can vary with respect to the UAV-based image analysis part, right? So as I said, we have one objective to develop, because this is one of the research gaps that we have identified. So we have developed one data set, that is the NITR drone data set, which primarily focuses on these two objects, that is the vegetation as well as the I would say the road extraction through semantic segmentation based computer vision techniques, right? So we have manually fly our drone, because in at NIT Rourkela we have one laboratory that is primarily focusing on UAV based image applications, right? So we have our drone, we have barely used the drone DJI Phantom 4 back that day, and we have fly it over our campuses. We have a campus of around 1,000 acre of campus. So we have fly it out over there, and we have identified the images uh, which are particularly can be responsible for uh, like uh, taking the constraint that we have received through the extrinsic challenges, and we have manually annotated around, I would say, 500 images, of which we have in our dataset we have only present 310 images, and they are of size of 4,000 cross 3,000. And basically we have multiple set of image resolution in our dataset, and yeah, the number is quite low in terms of the other available dataset. But if you'll see or compare the semantic drone dataset that we have seen earlier in the earlier slide, that has around 500 something, or that UDT has around 168 something. So yeah, so basically the that number is not exactly matters at that particular time, because you can have you cannot directly give the input of this particular images that are being captured by the drone dataset to your deep learning models. They have to go through a number of pre-processing techniques so that you can get your model trained, right? Now, once the dataset has been prepared, actually uses the cues from the encoder decoder based architecture such as UNet. You will find some kind of similarity with respect to that, because UNet was the best performing model that we have seen in terms of this drone data set, where it was able to achieve around 76% of accuracy. Now, by tweaking it in some way or the other, we have changed the internal portion of the UNet and uses some of the cues on top of it, and we have developed this model, and that help us achieving around 85% of accuracy. So there is a bit of improvement over there. However, still some issues are there with respect to the scaling related issues, which you may not find in a satellite based images, right? So this issue definitely would be there in terms of a UAV, because UAV may fly at different heights and may capture the same items from a different heights, right? That definitely give you the scaling related issue. Now we have deployed multi-scaling architecture with the help of this particular superpixel technique that we have first explored during the research work of satellite images. Right now, it is also like as you know that our primary goal was to develop an architecture of the framework which should have very less number of trainable parameters and would be feasible enough so that it can be deployed over a drone to perform the task in real time. So here if you'll see, our whole work started from a deep learning point of view and comes at a point of view of your IoT edge computing perspective, right? We have to we have to make a model in such a way that it should be deployed under the resource constraint environment such as an UAV and can perform the work in real time, right? So these are the whole work that we have actually conducted till 2023, and we are conducting we are still conducting research on top of it. We have research work on research works that I'm able to showcase over here. Now let's deep dive into this particular first task, that is the satellite IoT based image extraction techniques for road detection and road classification. I would rather say only this is the road classification we have not explored, because the data set that we have compared it out here are only for the road, right? So we have like identify at this particular point of time we are actually exploring the different kinds of remote sensing image analysis fields, especially the satellite, how the satellite image analysis can be differentiated with your UAV platforms, right? So we have, for every task, you have to identify the resource and the objective for it, right? So the primary thing that I have told, that the satellites nor the UAV have the capacity to process their images in real time on a particular platform. So here, that gives us the motivation as well to have that particular that architecture or the framework to be developed. So we have proposed a 3-layer IoT architecture for satellite image based road extraction techniques with the help of the semantic segmentation image analysis. So here, if you'll see that, if you know that this particular IoT architecture comprising of 3 tier or 3 levels. So the edge level, which is basically for your case, for our case, it is we can say that we are the edge devices, right? Because we are more closer to that particular sensor, or the data itself is with us. But in satellite case, it start from the top and go towards the base station, because these are the peripheral satellites that may present beyond your stratosphere, right? So these are some of the satellites which are flying miles away from the Earth, and they are doing the pictures or the data, and they are sensing the data for the Earth, right? So they definitely have very little or no processing power, because they can only capture the items. Okay, so there we have we just analyze it, and we thought that can be an edge devices, right? So this is edge level. In the fog level, there is the intermediary satellites, where we can think of these satellites can have some amount of processing power, so that the super pixels, basically when you group some of the pixels or related pixels which shares the same amount of information, that can be called as superpixel. So the superpixel images can be generated and can be transferred to the cloud level, so that you can say that the not exactly the real time, but approximation of the real time image analysis can be achieved, because here these satellites out here can have little to no amount of processing capacity, so they can hardly process any kind of data. However, if some amount of pre-processing can be done in these satellites nowadays, uh, yeah, if you see the various space agencies, they are actually trying to achieve these things, right? Because if you'll see that if the processing can be transferred across different levels of satellites before reaching it to the base station, then you can simply employ the deep learning based techniques, because the base station has the capability. They definitely have the server out there having the good amount of, you would say that, deep learning engines such as the graphics cards, or same amount of the parallel processing can be achieved here in the base station itself. So if the task, the full task without burdening it at the cloud level, if that can be categorized or divided among these three levels, then we can go towards approximation of getting a real-time image analysis, right? So this is our basic idea. And uh, as I said, the superpixel image generation principle is proposed over here only to get it as a pre-processing semantic segmentation, right? Because this particular superpixel techniques is basically being efficiently used in various medical image processing and various remote sensing image analysis, where this generally being used as the semantic segmentation step. In our case, we have done the same, so that the final segmentation will be done through the CNN based architecture. So this we have employed here the simple linear iterative clustering algorithm, that is the slick pixel techniques, to get the job done at the pre-processing stage. And after getting the superpixel images, we have used them as the inputs towards the CNN based architectures, where we have employed the unit architecture directly without tweaking it, right? Now, the primary idea of using the superpixel is this. If you'll see this particular picture out here, that this original image for the training set as well as your validation set and the test set, if I combine them, so they are basically the more than 1 GB. Now, once we employ the superpixel architecture to get the superpixel images, now you can see the amount of storage space, the reduction it is providing us. It is quite low as compared to, now compared it with respect to 1.1 GB, and this is around 4 and 12, 13 GB. So there is huge reduction of the storage space. Now there is a question that whether these images are still capable of providing the good accuracy in terms of the final output segmentation. Yes, it is. So if you'll see out here, we are even getting better accuracy in terms of recall as well as F-score and the IOU as compared to the normal images. And the processing times is almost same. Now, our target is also to reduce this time as well, but it is almost same, right? Same thing with respect to different, like I would say the data set. We have employed 2 set of data sets and 2 set of encoder, because we have used the I'd say the one of the baseline architectures in semantic segmentation developed in the year of 2015, basically for image segmentation task. However, their use cases have been quite rapidly grown towards different areas, also the satellite, also the remote sensing image analysis portions. So if you will see this particular architecture is called as encoded decoded architecture, where this portion until this can be called as your encoder part. Basically, this last layer, it is called as bottleneck layer. However, this is also the part of this reduction process where the encoder module will reduce the size of the images by employing the number of or increasing the number of filters, which can finally be used as the input for this particular decoder part. Now, this is what? This is nothing but your image classification part, right? If I am going to employ a final layer as sigmoid for a binary classification, this will become a image classification model, right? However, we are actually uses the queue of the image classification model with the help of the encoder, and we are expanding the resolution so that final image output will have those pixel regions being identified or segmented with the help of the cues. Those are being analyzed by encoder part, right? So this is where if you'll see the encoder part, we have actually deployed two set of uh, backbones. There is the squeeze extension based your ResNext 50 as well as the DenseNet. DenseNet and multiple models of which we have used the 121. There is no such study that we have conducted back that day. That why should we use it? Just we have used it because of some of the research papers. We have seen that these are the best models out there. Okay. Now we have conducted the research and finding out the results on top of these two data sets. This is the Deep Globe and this MIT data set, right? And this is the hyperparameter that you know that one is your in your deep learning architecture, one is your trainable parameters, one is your hyperparameters. The trainable parameters are internal to the deep learning architectures, whereas the hyperparameters are this, where this will help you to learn the model that you developed, right? So it is basically help you tweaking those trainable parameters with the help of these hyperparameters, right? Where we have chosen like optimizer as the ADAM, that is the adaptive moment estimation optimizer, and out of multiple losses, we have actually experimental out that this dice loss performs better, right? And these all the items you have to initialize it first, and you have to perform some of the experimentation. Once you get the optimized value of initialization, you have to made it and you have to start training again, right? So all these things we have identified experimentally. Base size quietly depending upon your size of the GPU, that I would say your GPU memory, and this momentum you can have it or you can simply deny it. But as ADAM optimizer is primarily focusing on two parameters, one is beta 1 and beta 2. Beta 1 is nothing but this momentum part. So you have to initialize it, right? Now sigmoid activation function has been used at the last layer. Why sigmoid? Because this is a binary class, because we are only identifying the road regions over here. So we have deployed the sigmoid function. If it is a multiple class, then we have to deploy the softmax activation function. Softmax activation function is nothing but multiple sigmoid function, which can give you probability in terms of different classes that you can have, and on top of which one thresholding will be applicable, right? So, and obviously, as you are training a particular model, you definitely have to evaluate it, because until you will test that particular model, how can you deploy it over a particular practical scenario, right? So for which we have multiple set of, I would say, the evaluation metrics. One is your loss function that we have also used over here, that is the dice loss, okay? And similarly, precision, recall, IOU, and F-score. We have not included the accuracy because of some reason, because if as this is a binary class, the accuracy may not give you that approximation in terms of a particular segmentation task, where you have that imbalanced issue in your dataset. Because I am saying this as imbalanced because if you will see, uh, uh, if you'll identify that we have one classes, right? This is the class which we want to identify, and this is the background. So the pixel constituting towards the background class is more than that of the pixels for roads. So that creates the imbalances. So there is no use cases of accuracy when you have an imbalanced class. So this is our primary observation that we have, and we have actually found out this experimentally. And this particular case, 1000_5, where 1000 represents the number of superpixels you want to have in your image, and this is known as the compactness. Like, like in terms of how it will work. Like, is the set of, I would say, the pixels that it will look for in a particular step. This superpixel algorithm. So basically, 5 number of pixels will be identified randomly, and they will try to group it in some way, and in that order, it will give you the superpixels as 1000. The number of superpixels is 1000. So this is known as the compactness factor in terms of the mathematical word, and this is the number of superpixels that you can have in your algorithm. That is a superpixel algorithm, right? So these are the I would say the accuracy that the performance metrics that we have achieved in terms of the various evaluation and the experimentation. Now, yeah. So now let's move towards our next. That is the drone dataset work that we have. And this is one of the sample images, and we have identified around, like, we have annotated four classes, and we have used one of the I would say the annotation tool, that is the label me, which was actually developed by one scholar MIT in 2015 or 16, right? So now they have full software kind of thing that you can simply install in your system and can use it. But at that time, we are using some Python library packages, and we are annotating it. Now, this is 101 full scale images, of which they are being actually used for experimentation. Out of the 500 and 310 number of images that we have actually annotated, we have actually used 101 number of images, right? However, when we are actually deploying it in terms of the various baseline architectures, we through multiple pre-processing techniques, we have identified around 500 or something like that number of images for training, and rest around 400 or 500 images they have been kept for testing purposes. Okay, now this is the basic comparison. Our target was to achieve all these four things, and we have primarily focusing on these four attributes. Okay, now this is a sample image of our dataset that we have prepared with it, and still we are annotating it because we have to increase the size as well as the number of classes, because the segmentation can be deployed in terms of principle can be employed in terms of multiple classes. We have only 4 classes like that day, and yeah. So similarly, throughout the process, throughout the UAV-based image analysis task, we have kept our system setup, because these are the hyperparameters and the performance metrics same, so that also the system is also same, so that there may not be any kind of environmental factor from the system itself or the hyperparameter changes thing that can be that can actually hinder the process of analyzing the different kind of models, right? So these are the few models that we have deployed around 12, I think we have deployed at the time on top of this particular data set, and we have benchmarked it by analyzing them. And if you see the number of trainable parameters also we have highlighted over here, because this helps us to find out the best optimized model that can be there in your research work, which can practically be available for not having those issues like the degradation problem, vanishing gradient problem, and the overfitting issues in your architectures, right? So these are some of the full-scale segmentation, I would say, for your UAV-based segmentation uh, task. And yeah, only these two models we have found out that they have actually identified the boundary of each of the objects very sharply, and unit is the best performing out of it. Now, these are the conditions where the performance actually decreasing for baseline architectures. Now, basically, identifying these issues, we are uh, performing the the objective for the next task, that is the developing of the real segment architecture. The first architecture that we have actually developed for this particular road and vegetation extraction process. So if we'll see that this particular architecture is quite similar if you'll consider it overally. This is having the encoding path, or I would say that this is the whole encoder module. This is the whole decoder module, right? So uh, we have borrowed the cues. Also, the internal change of done it in terms of this internal block, where each of the layer of an unit uh, they have been used in terms of some skip connection, and we have actually merged them together so that the concatenation can be done on each of these layers. So one skip connection to the other like this inside a particular, I would say let's say this is a particular module in a encoder path. So there you can have those skip connection being merged together. Now the skip connection are only concatenated without using any kind of, I would say, the parameter based learning things. We are only concatenated them so that the issues of the vanishing gradient problem as well as those overfitting issues can be reduced, because by concatenating them we are simply avoiding the increase of the trainable parameters, which is the primary goal. Because if you have more number of trainable parameters, it would be difficult for a particular device where you have less number of computational power to process it, right? So this is the primary thing, and we have we doesn't tweak that much in the overall model. However, it will give you the same set of, I would say, that hyperparameter setup for the experimentation are maintained over here. Now, if you'll see that these are the state of the arts that we have already experimented it in the previous work. Then if you'll see that we have managed to minimize the trainable parameters, and we are keeping it around 11 million parameters approximately, and quite less. If you'll just erase this one and the rest of the part, that this is quite lower as compared to the other architectures, right? And we have analyzed them. We have analyzed in terms of the multiple, I would say, your performance metrics. Also, we are evaluating the time per images. This validation image, or can be said as the testing image as well, because we have uh, find out the like validation portion of the images are being captured from the training set itself. Now we have only two sets, that is the training set and validation set. So validation set is nothing but the tail one, right? Now if you'll see that these are the performance measures that we are actually achieving, and in terms of the qualitative results, that you can see that each that out of this baseline architectures. Like this is our proposed. These are the baseline architectures. They are not able to identify those small corners right over here. This is the ground truth picture, right? This is the actual picture, the ground truth, and this is the proposed one, and this is the rest of the picture. One is unit, then this is your FCN 16, this is FCN 32, right? Same thing we have actually deployed with respect to two data sets. As I have told earlier, we have also included the UDD, one Chinese university that they have prepared it. We have also included it that as a comparison based process. So we have included it and we have identified that these are the issues. However, as I told, that multi-scaling issues is still pending. So here in this particular process, we have actually employed the multi-scaling based learning, feature learning. So we have deployed multiple set of our, I would say, your aerial segment architecture is, and we are only focusing on passing those changes with respect to the images. The size of the images are being changed and they are passed to the architectures, aerial segment, and the model has been captured as well as this. This is the whole architecture that we have proposed that day, without focusing on the filter, changing the filter size. We are primarily focusing on passing out the image as an input towards the architecture by changing the resolution itself. Okay, like this way. And finally, the concatenation has been done. And the final layer, the output has been received, and they have been compared to get the prediction. It will definitely enhance your output, because if you can see that we are getting an 86.5% of IOU as well as approximately 90% of EBSCO. However, if you'll see that the number of trainable parameters goes on increasing, because we have deployed about 4 number of these aerial segment architecture, which will give you around 40 million number of parameters. This is also one issue that we have captured, because we want to reduce the number of trainable parameters. So that is where this is the last task that we have done in terms of changing the convolution layer in your aerial segment process. We have, instead of the standard convolution techniques, we have simply used the depth-wise separable convolution techniques, which will reduce the number of trainable parameters up to a significant extent. The architecture is totally same. The layer in between where the convolution have been employed, they have been replaced by the depth-wise separable convolution, right? Now, if you'll see, we have managed to get around 2.5 million number of parameters in our architectures without much affecting in your accuracy. Yeah, some of the effects definitely you will be able to find it out in terms of this high IOU, because in the last case, in your multi-scale architecture, it is around 86.5. Now we are getting 82. However, we have managed to reduce the number of trainable parameters up to 2.5. Now, if you will, I don't have that, I guess. Yeah, actually, we have tested it out, this particular architecture, in edge computing device, that is your NVIDIA Jetson, and we have one drone. I have actually extended this work in my postdoctoral phase, and we have actually designed one drone. We have mounted that particular particular NVIDIA Jetson Nano module on top of that particular drone that we have assembled, and we have tested it out for this particular. And we've seen it you will find out the FPS frames per second is around 25. Okay, in a 4 GB Jetson Nano module. Now we people different kinds of mode there's an orange is so like its range starts from 4 GB to it can go up to 20 plus GB. So you can imagine the changes that you can achieve with respect to this kind of architecture as well as the devices, the edge computing devices, right? So like yes, we are managed to uh, reduce the number of trainable parameters, which obviously is our target, so that it can be deployed over the devices itself for performing the real-time task, right? Also, reduction help us to reduce the overfitting issues, the competition. Now, so basically the thing is that I would like to express without getting research folks, because once you start getting into this research area, I will definitely find pretty good problems out here, right? As I told you, currently we are working on this disaster management thing. So scenario will give or your interest will give you those problems, right? So yes, or wants to see or simply try to identify or get a like the applications we are focusing on currently. So you can simply go on like focus on the particular domains and identify the research issues and targeting those areas, because most of the researchers they try to focus on those areas where data set is available. But I will definitely tell you that if data set is not available in that particular domain or in research area, you try making it out, because that will definitely that I have shown you over there. They are nothing but CNN based architecture. However, you have currently the transformer based architecture, right? So like the vision transformer architecture we used to tell them like VITs has the fundamental issue of getting a huge amount of trainable parameters, which are still creating issues in getting the data under this that computational like constraint scenarios, like the IoT devices or the UAVs that I'm telling you, right? So there itself, there is a quite open area where you can simply work on developing lightweight deep learning vision transformer frameworks that can be employed for this task, that UAV based task, right? So like as was as I can as you know that the research has been like just in a rapid way, right? Back in 1980s, we have the first neural networks that is being developed, the deep neural network that has been developed by Fukushima, I guess. I'm not able to recall the scientist name. And after like two variants of those are there, like they have been like the transition is like 3 years, 2 to 3 years, right? So we get a new set of models in a very few days. Like the it is evolving in a rapid way. So everyone, please get into this particular research domain as quickly as possible. The machine learning engineers, the researchers, the faculty members. So yeah, if you like, if you have any kind of doubts or any kind of conversation that you want to have in this particular session, you can simply contact me in this particular emails or the phone numbers. Okay. Thank you very much.
I request participants.
Dear participants, if you have any query, please. Sir is available.
If you don't have any queries, we can wind up the session. I would like to thank Dr. Tanmay Kumar sir for their excellent presentation. We all found it very informative and engaging. Your insights into AI, ML, DL, and data science were particularly helpful. We appreciate you taking the time to share your expertise with us. We look forward to continued collaboration and hope to organize more such enlightening sessions with you in the future. Thank you, sir. Thank you so much.
Thank you very much. Thank you very much.
Thank you, Tanmay sir, for your acceptance. And your session is
Thank
nice.
you.
And we'll share the your feedback and everything to you, sir. Nice to have you in the
Sure,
session,
sure,
sir.
sure.
Thank you so much, sir.
Thank you very much. Yeah.
Dear participants, we'll share the feedback link. We already shared in the chat box. We shared the feedback link and attendance. Kindly fill the form. Based on the attendance only, we'll provide the certificate. Thank you, one and all.
Okay. Next session will be start by 2 o'clock today. So everyone please join at 2 o'clock. Thank you all.
Dear participants, you are sharing, you are raising your hands now. If you have any queries, please share through the chat bot. We are ready to help you. Do you have any queries related to feedback link or any schedule? Please. So many of the participants are raising their hands. We don't know the reason why. And small change in the schedule. Afternoon session we are going to start at 1:30 p.m. And we shared the feedback link through the YouTube link also. Share link. No need to worry about the feedback link. The link will be active up to the evening. You can fill. We shared the feedback link to the YouTube also. Kindly go through it. Link repeated a bit now. Dear professors, we are sharing the feedback link in the WhatsApp group also. Many of the faculties are not able to see the chat box in their mobiles or computers. So that's the reason we are sharing the feedback link in the WhatsApp group. Thank you all. And we are going to start the session 2 by the 1:30 p.m. today. Kindly join in time. Thank you all.